guys, today we're going to be talking through the 10.1 notes part 1, and this is all about what is a mole. So I've talked about a mole a few times, but today we're going to dive into what it really means. So before we get into that, I first want to ask you, what does it mean to say a dozen? Like, if I told you that I ate a dozen donuts this morning, not only would you be impressed, but you would know that I ate 12 donuts. How did you know that? Because a dozen means 12. So what if I said I had 4 dozen donuts? Again, you'd be really impressed, but you would also know that it meant I had 48 donuts because 4 dozen is 4 times 12. So we learn numbers like that related to words because it makes life easier. You can say a dozen eggs, or you can say, a dozen bagels, whatever it is that you want to talk about a dozen with. But in chemistry, we use this thing called the mole. And you might know a mole by the animal. It's like a little rodent-like looking thing. But in chemistry, we use the mole as a way of grouping many small things into a measurable amount. What I mean by that is when we talk about atoms, they're so incredibly small. If you guys remember from when we first discussed the atom is so small that you really can't even, the human brain can't quite comprehend how incredibly small it is. So you need a lot of them to be something you can even measure, like to be something you can even start to see. You need a lot. So that a lot is a mole. And by a lot, what I mean specifically is a mole always has 6.02 times 10 to the 23rd things in it. Remember how a dozen has 12? Well, this is how many a mole has. A mole has 6.02 times 10 to the 23rd. We call this number Avogadro's number, so here is Mr. Avogadro right there. He's not actually the one that came up with this number, but he's given credit because he's the one that started doing the work on it. We'll talk more about that when we get to gases. And when we say 6.02 times 10 to the 23rd in chemistry, we're talking about the number of representative particles. We're going to get to that in a second. Let's first talk about how big a mole actually is. All right, what if you had a mole's worth of soda cans? If you had a mole's worth of soda cans, you would have enough soft drink cans to cover the whole surface of the earth to a depth of over 200 miles. Just think about that. If you looked up, 200 miles up would be all soda cans. Okay, what else? What if you had unpopped popcorn kernels? Like, not even the big popcorn, just the little itty bitties. So if you had unpopped popcorn kernels, if you had a mole of them, if you had 6.02 times 10 to the 23rd unpopped popcorn kernels, and you spread them across the United States, the country would be covered in popcorn to a depth of over 9 miles. 9 miles of popcorn kernels. And that's just if you put them in the US. Okay, how about if you were able to count atoms? So if you had a mole of, say, carbon atoms, and you could count them, and let's say you could count them to the speed of, you can count from 1 to 10 million in a second. Like 1 Mississippi. You just counted all the way till 10 million. It would still take you just under 2 billion years to count all of the atoms in 1 mole. So a mole is really big. And again, the reason we need something so big is because the atom is so small that we need a whole heck of a lot of them to do anything on the human scale. So 1 mole, as we said, always has 6.02 times 10 to the 23rd representative particles, or things. Well, what are those things? It depends on what you're measuring. Let's say we have a mole of carbon. If you break up carbon into its representative particles, or the pieces that represent it, then carbon is going to be made out of 6.02 times 10 to the 23rd, because you have 1 mole. But this is going to be atoms of carbon. So why is it atoms of carbon? If you look at this, this only has 1 element, and you only have 1 of them. There's no subscripts. So if something is in its elemental form, it's going to be made of atoms. And when I say elemental, I mean just 1 element and no subscripts. So there's only 1 C there. What about 1 mole of H2O? Well, H2O isn't elemental. You've got hydrogen and you've got oxygen. Plus you have another hydrogen as well. So you have 2 hydrogens and an oxygen, in fact. So that's going to have 6.02 times 10 to the 23rd molecules of H2O. Why is it molecules? Well, it's made up of molecules when it's a compound that's covalent. And if you remember, covalent, there's no metals. So between hydrogen and oxygen, none of that's a metal, so it's no metals, covalent. Also, just notice that diatomic elements, when they're by themselves, those are going to be made of molecules. So those Brinkelhoff guys, so if you have like just bromine, bromine's always Br2 when it's by itself. Since it has that subscript of 2, then it's actually bonded together, so it is a compound. What if you have 1 mole of sodium chloride? This is table salt that you put on maybe if your chicken didn't taste right. So let's say you put 1 mole of sodium chloride on your chicken. I hope not, that would be way too much. But let's say you did. You would have 6.02 times 10 to the 23rd formula units. This is a funny one, and a lot of students forget this one. So formula units is when you have a compound, so see how there's 2 different elements, so that's what makes this a compound, and it's ionic. It's ionic because it's made out of ions. It's made out of things with charges. Sodium has a +1, chlorine has a -1. Those are ions. You can also remember that it starts with a metal. If anything starts with a metal, it's formula units. Now, sodium chloride actually breaks up itself into 6.02 times 10 to the 23rd ions of sodium and 6.02 times 10 to the 23rd ions of chlorine. Now, how did I get that? If I have 1 mole of this whole thing, within that, I've got 1 mole of sodium and 1 mole of chlorine because my subscripts here are technically 1. If I had different subscripts, I'd have more than 1 mole. So we're going to build this thing called Moleville. And Moleville is just going to be this map. It's like a thinking map. So it's to help organize your thoughts onto how to do these kind of problems. We're going to start really basic today. So in your notes, guys, I want you to draw a circle in the center. Leave room around it, plenty of room, but if this is the page that I gave you. And in the very center of this circle, I want you to label this as Mole City Hall. So if you are a mole, this is where you're hanging out, right here in the center. All right, go ahead to the top right corner and draw yourself another circle. And this circle is going to represent in your Moleville, this map of how we do mole conversions, Representative Particle High School, RPHS. And at RPHS, there are only 4 classes you can take. So go ahead and draw a line down, and 1, 2, 3, 4 lines for the classes. So what classes can you take? You can take atoms, ions, formula units, or molecules. All right, between these 2, we're going to need a road to connect them. So here's your road. Now the next part is really, really, really important. Make sure that you draw the, or write the right units in the right place. So right next to Mole City Hall, right here on the road, I'm going to need you to write 1 mole and then ... for a ratio. So for every 1 mole, we have 6.02 times 10 to the 23rd representative particles. And in Moleville, this is just written on the ground. They like to write stuff on the roads to help you. Also, hanging out here is, oh wait, that doesn't work. There we go. Mr. Avogadro is just hanging out. He's the principal of Representative Particle High School. He's got a stop sign to make sure everybody's using the right units. Okay. Take a second, make sure you have this fully copied on your Moleville map. Make sure you're leaving room over here for everything else, because we're going to add to this map for the rest of this school year, basically. So freeze the video if you need more time. So how do you use Moleville? So I've taken a little picture of Moleville. So here's the deal. You find the units of your known and your unknown on the map, and you're going to track how to go between the 2 on the map. Because if you notice, we've got our conversion factor here. So you'll see how to use that. Use the unit converters on the map roads, and always divide by the unit you see first so it'll cancel properly. So let's do some practice problems. If you're given 4.8 moles of glucose, and glucose is C6H12O6, that is the sugar that you convert all your food to, how many molecules are present? So first you find the unit of your known and your unknown. And your known is you have 4.8 moles of glucose. So where is moles? Well, moles are in your Mole City Hall. And you're trying to find how many. So, I don't know, how many what? Molecules. So find molecules. It's right there. And then how do you go between the 2? you'll notice this is the direction. So you're starting in moles and you're going over here to representative particle high school. You're taking the molecules class here. All right, now we're going to set up our stoichiometry by writing what we have known first. I know 4.8 moles of glucose, and then you have to set up your X line, so multiplied by some fraction. The rule for Moleville is whatever unit you hit first goes on the bottom. There's one thing that's key that's not written in Moleville, which is what the substance is. So whenever you write anything in your stoichiometric calculations, you always want your number, your unit, and your formula. NUF, number, unit, formula. So make sure you have NUF written everywhere. This doesn't have the formula because it could be anything, and that's something you have to make sure to write in to make sure you're canceling things properly. All right, so if we go here first, the first thing we hit is 1 mole. Whatever you hit first, that's what you divide by. So on the bottom of this fraction, because on the bottom of fractions means divide, you're going to put 1 mole of glucose. On this road, you can't change the formula. So the N, the number, and the unit are given, and then the formula has to be the same for both. So since we put glucose here, it has to be glucose on the top. Next thing you have is 6.02 times 10 to the 23rd molecules of glucose. So remember, you divided by what you hit first and you multiply by what you hit second. Make sure you add your formula for what you're measuring and it's the same for both sides. See how this has C6H12O6 and the bottom has C6H12O6? You can't change the substance if you're comparing molecules to moles. So this road here has to keep the same stuff. All right, so the next thing you can do is see if anything cancels. Do you have anything on the top and the bottom? You do. You have moles of glucose. So those go away. Multiply by the stuff on the top, divide by anything left on the bottom. We just have a 1 on the bottom. You never have to divide or multiply by 1. It won't change your number. So go ahead and type this in your calculator and see if you get the same answer I do. Did you get 2.9 times 10 to the 24 molecules of C6H12O6 or glucose? If you didn't, go ahead and ask a teacher so you can make sure you get your questions answered. If you did, you can move on. I also want to point out the significant digits. So this has 4.8 that has 2 digits in it, so I wanted to keep 2 digits in my answer. I think it was like 2.88 or something. I did it a while ago, so that bumps the 8 up to a 9. Let's do one more sample problem. A balloon is known to have 3.4 times 10 to the 22nd atoms of helium inside it. How many moles are present? So the known is going to be 3.4 times 10 to the 22nd atoms of helium. Atoms is your unit. So you find where on this map does it say atoms, and you'll see it's right here. It's part of representative particle high school. It's a representative particle. Atoms are particles that are represented by matter. So what are you trying to get to? Well, the question is, how many moles are present? So that's going to be in Mole City Hall. So here's how I would get from atoms to Mole City Hall. You use this same road. Now we're going to be using different roads later. I realize it's kind of a bit of the same, but for now, just make sure you get used to using this road. Whatever you hit first, you divide by, and whatever is second, you multiply by. But first we have to write our known. So there it is, 3.40 times 10 to the 22nd atoms of helium. Notice you don't have to write of here, by the way, so it's just atoms, helium. The of is known or understood. Next, you write your X line, which tells you you're going to multiply by some fraction. And what goes in that fraction? Well, whatever you hit first is what you divide by. So if you're going from representative particle high school to Mole City Hall, the first thing you hit is that Avogadro's number. So that's going on the bottom. It's 6.02 times 10 to the 23rd representative particles, but which representative particle, which class did we take? Atoms. So 6.02 times 10 to the 23rd atoms, and don't forget you have to put the formula, helium. It needs to be the same as up here, so it'll cancel. Also, once you write the top, so the top's going to be 1 mole, and it has to be 1 mole of helium, because you can't change the unit in here. So if you have moles compared to atoms, you can't change the unit. It has to be, you can't change the formula. So helium and helium, top and bottom. Okay, is there anything that can cancel? Yeah, atoms of helium are both on the top, there, and on the bottom, there. So they cancel. You're going to multiply by anything on the top, so 3.40 times 10 to the 22nd times 1, but you don't ever need to multiply by 1, and then you're going to divide by 6.02 times 10 to the 23rd. Here's the one huge thing that people mess up on. When you divide by Avogadro's number on the bottom, you want to use that E button. And if you can see it, it is right above there. So you have to press second and this button. It depends on the calculator. Some have a big E for it. And that is 10 to the. So when you type this in, you would type 3.40, no multiply and no 10. Just write to E22. And then divide, because this is the bottom, 6.02 E23. So again, no multiplying sign, no 10, just 6.02 E23 equals. You're going to keep 3 sig figs in your coefficient to keep things consistent. So you should get 0.0565. Here are your 3 significant digits, and it's moles of helium because that's the only unit you have left. Okay? Best of luck working practice problems. Let us know if you have any questions.